Multicasting is one of the way in which the traffics go to destinations. You might have heard about multicasting many number of times, but you may not have a clear picture how it works. We know what is unicast, sending traffic to a particular destination. You know the IP address of the destination, you send the traffic to that destination. The IP address belongs to a computer or any device. It's the part of a single device. We call it as unicast. And when we send the traffic to an address which belong to anyone, we call it as broadcast. Anyone who receives the packet will claim the ownership. Such packets are broadcast. And in layer 3, we use this 255, 255, 255, and 255 broadcast address. Other than this, every subnet will have their own broadcast. This is global broadcast. For example, if you take 192.168.0 network, this is the broadcast of that network. Any traffic that are sent to this address goes to any device in the subnet. All will take the ownership for the packet. But what is multicast? What is multicasting? Multicasting is sending to group. Group? Which group? The group of devices that are eligible to receive the packet. Okay, how do we identify that group? You have a special multicast address to do that. So any address that is ranging between 224 to 239 can be used to identify the group of device that needs to get the update. So multicast range 224 to 239. We give this address on top of the address that the device have got. So the device may be in any subnet, any destination, any network. Some may be in 10.1.0.0 or 10.1.1.1. Another group member may be 10.2.0.65. Another may be in 10.50.0.200. If you see these computers, they don't really belong to same network. They're all somehow connected through some routers. So when anyone send a traffic from here, from A, when someone send traffic from A, and only these three destinations you want to receive the traffic, you need to form a group. You see, we need to now provide a common address for these three members. They all have their own individual address. On top of that, we are going to give an address like this, 239.1.1.1. How do we provide an additional address? ICMP is used here. Sorry, IGMP. With the help of this protocol, Internet Group Management Protocol, we group. Now, when A sends the traffic from the source, let's say 10.0.0.1 to the destination 239.1.1.1, up to here, the traffic goes as a single copy. Single copy. But after reaching here, it replicates. It makes additional copies depending on the topology. Now, one copy of the packet goes this way and reaches this destination. Another copy comes up to here and take another duplication and then goes here and goes here. And then at last delivered here. So the advantage here is in this topology, in this part of the network, it's not three packet for this three destination, it's a single packet. And in this link, it is not three packet, it is single packet. In here, single packet, single packet. Here, two packets. Now, even here it is single packet. That's the beauty of multicasting. Even if you have 100 destination, you're not going to send 100 copies of the same packet. Only one you're going to send till the diversion takes. This is the biggest advantage of multicasting. We don't waste bandwidth. Though the destinations are too many, you are sending single copy. And that single copy can go to the rendezvous points, the meeting points from where they can decide how many copies they should replicate. And thus it reaches the final destination. So multicasting reduces the bandwidth utilization. Not only bandwidth utilization. These routers on the path, they are not processing three different destination networks in order to decide on the exit forwarding port. Only one destination. So even CPU is getting reduced a lot. Multicasting is wonderful. All right. So we have seen the advantage of multicasting. Now how this is possible. We already learned one protocol, IGMP, which is helping to enroll, take membership with a group. That is on the end device. That's on the routers where the end devices are connected. And again, this need not to be a router. This can also be a computer with an application which is allowing you to use IGMP. So this port here, it is a router. But in the real world, we will see a lot of people installing a software in order to join a group call. And that group call will use IGMP. And the group call is going to have a multicast. Right now I am speaking to you. I'm the source of the multicast. And you both are getting it simultaneously. Which means that Google Meet have enabled you both to join that group. You have joined a group. There are many groups in my laptop, but not all the groups are active now. And no other group members are able to listen to this class because they don't belong to, they didn't join the group. Now, when one of you speak to us, you become a source and we become the group member. When the other person starts talking, you become the multicast source and we become the group member. We call it as bidirectional PIM, which is discussed later. Anyone can be a source at any point of time. And the previous source can be a group member. Fine. Now, for this multicasting, there is another protocol called PIM involved in this, protocol independent multicasting. And the PIM runs from this portion to this portion of the routers in between. So all the routers in the path must run PIM. All ISPs will have this PIM enabled always. So protocol independent multicasting is the protocol that helps to discover the multicast running routers, the multicast path, via which the multicast traffic can be routed. You see, though it is an IP packet, they are multicast packets. So you cannot use the IP route, you need to use the multicast route, M route. M route, multicast route, is possible only if the path has got PIM running. So a tree gets created. You see the tree? This is the root of the tree. And this is one branch of the tree. This is another branch of the tree. This is another branch of the tree. This is another branch of the tree. A tree has been source-based tree is created because the destinations are here, here, here. If in case I don't have this group member here, I have this computer, but this did not join the group. So what happens is when a packet is sent from here, Wherever the PIM is enabled, let's say PIM is not enabled here, the multicast traffic don't go that side. It goes all this path. Wherever the PIM is enabled, it goes. But this router, what it will do, it will not accept the packet. It will prune it. Though the packet is hitting the port, it reads and finds a meaningless packet coming in and it drops. It is like someone trying to sell you some product and you say, not interested, not interested. Pruning. Again, after some time, there will be attempt made by this PIM. Again, this router is going to say, not interested. No one to use your packet. I don't want your packet. But as soon as you enable IGMP and join this group, this time when the packet attempt made, this says, yes, I accept you. So when there is no member to receive, pruning happens. This we call as flooding and pruning. Though there is a member or not, the flooding has been made, the attempt has been made. And the attempt is not successful because there is no one to accept it. We call this as pruning, flooding and pruning. But this method of flooding and pruning, which is called as dense mode, is no more in the industry. Maybe here and there you may see, but according to my knowledge, not many people keep this mode as a feature in their devices. The manufacturers stop using this dense mode option. Low-end devices, they may have it, but not everyone is ready to use it. And high-end devices, they don't even have it. Because in high-end devices, every single second and every single bit counts. If a customer enables this dense mode, and because of that the efficiency goes down, it will create a bad name for the vendor only. So vendor says, we don't support dense mode. Later you should not come and say my device is not good. When we use the mode called sparse mode, we can avoid this flooding and pruning, which can reduce the waste of bandwidth and CPU. We call that a sparse mode. So when a packet goes here, it's getting flooded in the dense mode. Sorry, it gets pruned in the dense mode. Now, when you have a sparse mode, the packet won't even go this direction. No, not allowed to go. This router won't allow. Why? This router knows very clearly there is none to receive your multicast packet. This router will know, every router will know the direction where the members are connected. Sparse mode can avoid flooding on the links, flooding over the links where the group members are not present or absent, which is really good. Now, how the sparse mode works. We have to configure one of the router to be a midpoint for both source and the destination, for source and the group member. We need to configure one of the routers somewhere in the middle as a gathering point, as a midpoint, as a rendezvous point, so that the source can come and tell, I'm the source for this group. And the group member will come and say, I'm the group member for this source. So once the source and group meets, the source now knows where the group members are located so that the traffic can be sent only to those locations. So the gathering point, the group meeting point, the group member and the source, the gathering point, we call it as rendezvous point. Let's assume that we have this router configured as the rendezvous point, gathering point. Every router should know this is the rendezvous point. We have to go and tell every single router that this particular router, let's say this router's IP address is 3.3.3.3. And this 3.3.3.3 should be reachable from all the routers. Now we have to tell every router that this 3.3.3.3 is this 3.3.3.3 is the rendezvous point. Yeah. So we have a rendezvous point known to everyone. Now, as soon as you join this group here, here, and here, these routers will go to rendezvous point and say, hey, I'm coming from so and so IP address. Let's say this one is 30.0.0.1. It will say, I'm coming from 30.0.0.1. I belong to 239.1.1.1. And this guy will say, let's say this is 60.0.0, and this is 50.0.0. This guy will say to this guy, I'm coming from 60.0.0.1. I belong to this group 239.1.1.1. So now this rendezvous point knows that there is one receiver on Ethernet 0 interface, one receiver on Ethernet 1 interface. So it says, I don't know the source, but there is a group member 239.1.1.1 over the interface E0 and E1. Now rendezvous point knows about the receivers. And this router here, in its multicast table, this says, I don't know the source, but there is a group member 239.1.1.1 on E2 interface, only on E2 interface. This is how, flooding on E1 is avoided, because it knows via which the request came, the enrollment. This is the direction it came. So all these routers in the path knows the group members. They all know the group members, where they are located, which interface the packet, if sent, it will be useful. But what they don't know so far is the source. Now, as soon as the source comes, let's say this 10001 is the source. As soon as the source comes, this will learn 10001 here for this multicast. And now the source and group member knows each other through this rendezvous point. The process of knowing, even this router in the middle will also get the info from the rendezvous point saying 10001 is the source of this. So now if you notice, because they know the exact locations, the tree will be established only like this. Now let's assume rendezvous point is here. In that case, if this is the rendezvous point, just for instance, I'm telling you, if this is the rendezvous point, only the first time to know the source and the group member, it will take this long route. Make sure the PIM is enabled on all this thing. Yeah, PIM is enabled. What if I'm just trying to say, what if the rendezvous point is not in the path? It's away from the path. The original path is this, but it is away from the path. So the source and group member will learn each other through rendezvous point, and then they will find the best path to reach themselves, and they will take the shortest path. So only the first packet will go through the rendezvous point, after which they use the reverse path forwarding, meaning they check the routing table to reach the group member and group member to reach the source, and they find the shortest path. They will not always go through rendezvous point if rendezvous point is not in the path which is shortest. Right? So what I have said here is there is a rendezvous point. And this rendezvous point we only decide. And you go to every router and configure rendezvous point manually. That is one method. The other method is already PIM is running everywhere. You can use PIM to advertise it. Yeah, PIM can advertise the rendezvous point. There is also one more Cisco proprietary called Auto RP. These are the ways in which the routers can dynamically learn rendezvous point. But preferred is use the BSR, meaning bootstrap router, meaning PIM itself will advertise the RP to every router that runs multicasting. The other method is statically you go and tell every router who the RP is. You can also have multiple RPs, and you need to sync between the RPs so that they can work together. So like this, we are going to see in the lab all that you have learned. First, we will see the dense mode, and then we'll create a rendezvous point, and then we will first statically go to every router and configure RP and see how it works. Secondly, we'll enable BSR, and we'll see how the RPs can be learned dynamically, right? Fine then.